So I'm really glad you guys laughed a bit because I have a few jokes in my slides. And if it was just deadpan silence, it's like, oh, I better skip those slides. Okay, so I'm Dan. I'm going to be talking about deep learning in TensorFlow with a bunch of cool visualizations. I'd like to ask first, just to get a sense of where the audience are, like how many people here would find going over deep learning to be like redundant and not that interesting? Okay, a few people. I appreciate the honesty. Like, I mean, I hope that it will still be interesting for you because I have some like cool charts and figures and graphics that are new. And how many people would find an intro to deep learning like useful and interesting? Okay, so there's a fair number of people. I won't feel bad that I'm just like horribly boring you all with the basics. So a bit about me first. My name is Dan Mané. I actually came into machine learning from a weird direction, which is to say a background in data visualization. And on the TensorFlow team, so I'm part of Google Brain, which is the team within Google that's doing a lot of deep learning research and has also created TensorFlow. And I'm specifically responsible for Tensor Board, which is this visualization framework that's built into TensorFlow. And if that's new to you, don't worry, I'll also show it off. But first, let's talk about deep learning. So we really mean deep neural networks for the most part. And for this, I'm going to use a bunch of materials made by my friend and colleague, Chris Olah. If you haven't encountered his name before, he has a really great blog on deep learning. So if you feel like, oh, wow, those charts were super helpful, I highly recommend you check it out. There's lots of great explanations there. So artificial neural networks are kind of inspired by regular neural networks. I Googled for what is a neuron, and I got this image of a typical neuron. And you can see that you have like, okay, it connects to other neurons over here, and then it, if you know a bit about neurology, which I don't, it will sort of get impulses from other neurons and maybe fire, and then trigger the other things it's connected to. So if we wanted to turn it into a simple mathematical model, we might get something that looks kind of like this. It has some connections to other things, there's some kind of black box, and then it outputs some signal. And we can make this a bit more concrete. We could say, okay, there are going to be weights on the connections. Maybe the neuron is going to have some sort of B, which is a bias that like it uses as an additional signal on whether or not it should fire. And we could make this a little bit more formal as this binary threshold neuron. So the way this works is you basically sum over all of the inputs times their respective weights. You add in a bias term. And then if it is greater than 0, you output 1, which is an activation. And if it's less than 0, you output 0. So this is an extremely simple model. But interestingly enough, out of this really simple model, you can build a NAND neuron. So you can look at this and just kind of persuade yourself that it simulates a NAND gate. And of course, you can really build anything out of NAND gates. So what this is telling you is that even if you take a very simple model, you get a universality result. You could build any possible function, any logical circuit. You could build a Turing machine out of just enough of these neurons. But the real question is, okay, it's great that we have this like way of expressing functions that allows you in theory to do anything. But how are we going to train it? How are we going to find the right point in this massive parameter space that will do something useful? And the answer is with calculus, courtesy of our most badass mathematical friend, Isaac Newton. My impression is that this is actually a pretty accurate depiction of his character. And to make it trainable, we're going to need it to be differentiable. So this binary threshold neuron is not really very good for our purposes because this is not a differentiable function. The derivative is always 0 except for when it's infinite. So we could replace it with some smooth function. Maybe you would use a sigmoid. In practice, people use something that's a little bit more hacky called a ReLU, but it doesn't really matter. And now we have this sigmoid neuron. So that's great. And we probably want to have more than one neuron because we need to represent things with a lot of information. So we're going to organize them into layers where you have now you have the input and then it maps onto a new set of inputs via some complicated set of weights, and then you have a bunch of biases for each neuron. And we can start to play around with this and reorganize it and realize, oh, hey, that's just matrix multiplication and vector addition, and then passing through a nonlinear function. So really, this is the core idea right now in neural networks, or at least in feed-forward neural networks, is we're going to have some input data. We're going to multiply it by a matrix. We're going to add another vector. And then we're going to apply a nonlinear transformation to that. we can look at that not as abstract algebra, but as geometry. So in the geometric perspective, if we have two neurons, we can imagine, okay, the neurons are going to take some point in a two-dimensional space, and then through the activation, it's going to map that point onto a different point in a different two-dimensional space. So we can start to look at the layer as doing three things to the whole space. First, we're going to stretch the space. Then we're going to shift it, which is the bias add. And then finally, we kind of twist it a little bit with our nonlinearity. So that's the whole activity of neural networks. We're going to sort of stretch things a bit, shift them a bit, and then squeeze them a bit. And the interesting thing about neural networks is that it turns out by doing lots of these stretches, shifts, and squeezes, we can start to learn complicated functions. So here's a simple example. We just want to separate these two curves. We could try to use a linear separator, and it's not going to be a very good solution because this is not linearly separable data. What the neural network does is it learns this sort of curve that matches the data. But the way it does that is by mapping the data set into a new representation where it is linearly separable. So in this case, we have just a single layer in between, and it sort of starts with its input. Then the hidden representation with the two new neurons is stretched and squeezed in such a way that it's separable. And then we can just output based on hyperplane separator if we want. So let's look at a slightly more complicated example, which is a spiral. This graphic is showing us taking, I think it's a 4-layer neural network that just repeatedly stretches, shifts, and squeezes the spiral until we have nice, easily separable data at the end. And my talk is going to come probably in short, so we may as well watch this twice. It's so interesting. OK, so that's very exciting. But what would be really exciting is if we had some sort of sweet like JavaScript interactive playground where we could see this happening in real time. And localhost is not available. What does that? Well, I guess I could just entertain you with my jokes early while I figure out how to reconnect to this network.
Is this visualization tool, is it available at all?
So, OK, this seems promising. This thing which I'm about to show you is not yet available, but we're going to release it very soon. Probably within the next week or two, we're going to put it on the TensorFlow website. So you can just think of this as a cool preview. OK, here we are. So what this is showing us is like a live training of a neural network. So let me first just explain what's going on here. We have a data set that we want to separate. In this case, it's a very simple like concentric circles. And we have a sequence of neurons. This one is showing us the sort of the input neuron, where we can see, OK, this one is just the Y position. This one is the X position. Then the first layer is going to learn some new transformations that are a combination of the previous layers. And in this case, it just has some sort of rotated planar separators. And finally, it's going to have an output layer here. And right now, it's just sort of a weird, goofy plane. It's not really doing anything very useful. So let's try training it. Now we can see that it's starting to shift. It's starting to figure out. And then very quickly, it gets the correct representation. And so we can sort of use this to get a visual intuition for what the neural network was doing. This first layer really was just able to shift around these planes a little bit. But it shifted around planes such that now you can take a linear combination or a near linear combination of these planes and successfully get the circle. And so it turns out we actually even have more neurons here than we need. We could take it down to just a single hidden layer with 3 neurons, and it will eventually get the correct representation. But you do need 3 neurons here. If you try it with just 2, it will kind of struggle endlessly, but it doesn't have enough information to represent the real shape. But it tries. That's better than 50%. And we can also look at this for harder problems, for example, the spiral. And it's just kind of fun to explore what these try to do. So let's see. It actually has a lot of trouble getting the spiral. which if you think about it, if you want to figure out a way to like deform these two planes to map onto the spiral, it's not an easy problem, and it tends to make some progress eventually, but let's see what happens. Oh, I took the learning rate down. Yeah, this is entirely local. This is just like another example of like, I ran this like 5 times before. I'm like, okay, it does something kind of interesting sort of quickly. So I can probably just like watch it go. But naturally now it's not obliging and it's just kind of like stuck on this, maybe we can split the data set in half idea. So maybe we'll kind of revisit this in a little bit once it has discovered something interesting about this data set. But now it's actually moving again. Okay, so I'll return to this, and in the meantime, I'll go back to my slides. Okay, so this is more or less the end of my introduction to neural networks, but I'm going to allude to some other interesting things that are happening in the field. So what I've shown is the most basic primitive piece of feed-forward neural networks, but there's a lot of different structures that are quite interesting. For example, convolutional nets. These are really useful in image recognition or any time when there's repeated structure. The way it basically works is you're going to tie a lot of the same weights so that you can learn, instead of, if you imagine that I'm showing you an image, if we were just doing the feed-forward neural nets with the layers and like in the previous diagram, you would need to learn anew for every portion of the image, like what does an eye look like, what does an edge look like, what does a curve look like. So the idea with a convolutional net is that the lower layers, we're just going to have a lot of repeated substructure. So it can learn one concept of a curve or one concept of a gradient that it can then apply everywhere. So basically all of the modern image recognition techniques are using conv nets. Then we have recurrent neural networks. These are capable of working with sequences of data. So the way it works is we have a single neural network that conceptually like loops back on itself. So that if I were to give you, say, you wanted to do a translation model, maybe you want to translate English into French, then what you could do is feed into the neural network one word at a time in sequence, and then it maintains state from one step to the next, so it can kind of remember like, okay, if your previous word was the, then that changes how to interpret the subsequent word. And then we also have LSTMs. This is a particular variant of a recurrent neural network where it now has a complicated internal structure. And the basic idea was that with recurrent neural networks, they're not very good at remembering things. So LSTMs have an explicit mechanism by which they have like quote unquote short-term memory and long-term memory. So the short-term memory is just as in a recurrent neural network, it just feeds forward from step to step. And the long-term memory, it has a gating mechanism by which the neural network can kind of learn when it needs to remember things and when it needs to forget things. So that this way it could, in the text example, it could pick on certain details in the beginning of a paragraph that maybe will be very important for determining what the semantics of the end of the paragraph are. If you wanted to see visualizations of this, there's a really great blog post called The Unreasonable Effectiveness of Recurrent Neural Networks by Andrei Karpathy. And in it, he sort of goes step by step with these LSTMs, kind of visualizing what pieces is it remembering and what pieces is it forgetting. So I highly recommend that. There's also, I'll just mention, a really cool result, which I don't have a diagram for, is neural Turing machines. So this is a relatively recent work by DeepMind to create neural networks that have differentiable strategies for essentially learning loops, algorithms, and writing to memory, where it's not just like one vector of memory, but it has a whole memory space that it can read to and write to and move around in. So they've had some success in teaching neural networks to learn algorithms. So it learns like basic for loops. I think it may have learned to sort. So just very interesting stuff. So that's neural networks. Now I'm going to talk a bit about TensorFlow. TensorFlow you probably all have heard of. It's Google's new open source distributed computational framework. And it's being mostly applied right now for deep learning, but it actually has a lot of broader applications. But first I'm going to talk a bit about the team that made TensorFlow, which is Google Brain. So Google Brain is led by this guy named Jeff Dean, who you may have heard of because he, among other things, came up with MapReduce, which of course Hadoop is based on. But MapReduce is actually, I mean, Jeff Dean is incredibly prolific. MapReduce is like one of many systems he created. So the external stuff is like LevelDB, Protobuf, internally Spanner, Bigtable, basically all of Google's great distributed database systems. He also built the first implementation of like Google advertising serving and worked on a phenomenal array of Google products and core technologies. So where the rest of the world has Chuck Norris jokes, you know, like Chuck Norris, what's a good one? Chuck Norris can slam a revolving door. This kind of stuff. Google has Jeff Dean facts. So some of my favorite Jeff Dean facts. One is the speed of light used to be 140 miles an hour. Then Jeff spent a weekend optimizing it. Compilers don't warn Jeff Dean. Jeff Dean warns compilers. And my personal favorite, Jeff Dean puts on his pants one leg at a time. But if he had a larger number of legs, you would realize his approach actually scales as O of log n. I really appreciate any crowd where I can make asymptotic runtime jokes. But the fun fact about how this applies is that Jeff Dean also designed TensorFlow. And TensorFlow is actually his second attempt at making like distributed deep learning. The first one was called Disbelief, and like it was successful, but it wasn't really good enough for Jeff. So about a year ago, we started working on this new system, and then open sourced it in November. So what is TensorFlow? Well, fun fact, you know, just this is an aside. There's a naive model of producing talks in which you start working and you have no slide deck, and then you finish working and you have one slide deck. So you'd think, okay, there's some sort of positive correlation between the amount of work you do and the number of slide decks you have. But in reality, if you don't work enough, you may wind up with 2 slide decks. And that is the situation I'm in since I didn't get all of my animations to transfer over to this JavaScript thing. So we go on to the second slide deck. So I'm going to take a very, very kind of literal approach to explaining what TensorFlow is, which is to say I'm going to explain first what's flowing and second what are tensors. Let me actually ask this. How many of you guys already know how TensorFlow works and like data flow graphs? You've been using the API. This would just be boring for you. Okay, approximately no one. That's great. Because like I said, my talk is going to come in under time. So really, like the more things I have to go over. Okay, so TensorFlow is all about specifying computational graphs. If I alluded to the fact that it's being used for deep learning, but could be, in fact, used for a lot of other applications, that's because it has this really sort of abstract, low-level semantical structure. So in it, you have these graphs, and the nodes represent computation. So in this case, I've made a node that represents adding 2 numbers and a node that represents squaring a number. And we can just feed in some numbers and kind of pass through the system, and we'll get our result. The nice thing about this is we could use it for a lot more than just addition and simple arithmetic. We could also use it, for example, matrix multiplication, matrix or vector addition, and sigmoid functions, which is to say that all of the pieces of neural networks we're going to get in this computational graph framework. And just for an example, you know, we might represent handwritten digits. Like this would be a number 1 in MNIST represented as an array, where the intensities are the pixel darkness. So that's what's flowing. That's the graph. What's flowing across the graph are tensors. Tensors are really just like the arbitrary dimension generalization of scalars, vectors, and matrices. So we could say this is 0 tensor, a 1 tensor, a 2 tensor, a 3 tensor. You can have arbitrary dimensionality of the data. So very commonly, you'll have like a 4 tensor for images where the first dimension is your batch size. So you're grouping lots of examples together for efficiency. The second and third dimensions are the pixel, like the actual position of pixels in the images. And the fourth dimension contains the color channels. So with that, we have data flow graphs. And we just need some added pieces. So TensorFlow is going to have a mechanism for storing persistent state. That is to say, like weights can be stored within the graph. Then it has mechanisms for bringing in input. So you can set up queues that will like read data out of a database and pass it through your graph. And then in the output, it makes predictions. So let's look at an actual example of a small TensorFlow graph to make this a bit more concrete. So this would be a small graph that has a single layer neural network. So here is the layer itself. At the bottom, we have a matrix multiplication and a bias add, and then a nonlinearity. So it's exactly the same basic pieces. And then maybe we need to go and take the hidden layer and convert it down to the number of classes we want to predict for a regression. So we would have here just another matrix multiplication, another bias addition. Some of the really interesting stuff about TensorFlow is what happens up here. So in neural networks, it's relatively simple to build a feed-forward neural network that just does inference or makes predictions. But what becomes a lot harder is training it. So I haven't really discussed the training of neural networks in my overview. But the idea is we're going to, because the neural network is a differentiable function, we can treat the whole function as producing an error as a function of the parameters of the network. So conceptually, like I have this little proto-MNIST network that's trying to predict handwritten digits. And I feed it all of the examples of handwritten digits that I have. And it does maybe a terrible job. Like it just has no idea what a 0 is. It has no idea what a 1 is. But I can now say, compute the mistake that it made and compute the derivative of that mistake with respect to all of the parameters in the network, and then start to minimize that. So what TensorFlow does that's really nice here is all of that work of figuring out how to compute the derivatives of your graph and minimize it, it handles implicitly. It's called auto-differentiation. So what that means is that you as the network designer can just specify like, okay, I kind of want these like feed-forward networks, feed-forward layers. Maybe I want one to be convolutional. Maybe I want to choose my loss function very, very carefully. But then all of the work of figuring out how to train that network, TensorFlow will do for you. So what happens in this example is we have some data that flows upward through the network. We make a bunch of predictions. And then we compute a loss function based on the predictions versus the actual labels in the data. And then it enters this sort of magical black box for us. And the result is that the network is trained, and we can keep on working with it. Back to the first slide deck. So one might say, OK, like that's great that this computational system you've described can train and simulate neural networks. But it also looks really complicated. Like in the previous layer, we just had like a matrix multiplication, bias add, and addition, and we just wanted to like glue these layers together. Why do we need to think about all of this other stuff? Why do we need to learn about computational graphs? And interestingly enough, actually the first approach that we took for doing deep learning at Google looked very different. Dist-to-belief really did just have a layer, and you kind of would say like, okay, I want this kind of layer, I want that kind of layer, I want this kind of layer. I'll plug them all together. Please like train it for me. And it was a much simpler API. There are a few advantages to this approach. One is that we want to be able to do really complicated things. And specifically, the Brain team has a lot of researchers who are trying to push forward the cutting edge of neural networks. And if you just give them like a black box that is a layer, it's really not good enough. So having this really low-level representation means that whatever kind of complicated neural network you can imagine, you can implement very naturally in TensorFlow. So like, there's no way you're going to fit a neural Turing machine into a layer-based, sort of straightforward layer-based system without a lot of work by the core developers. But here, anyone can start to tinker on minute details of the network and experiment with it. The other nice thing is that Jeff Dean, known from MapReduce, this guy really cares about how things scale across large clusters of machines. And the TensorFlow graph framework makes it easy to partition up the work either with data parallelism or model parallelism across lots of machines and lots of GPUs. And actually, earlier this year, we open sourced the distributed implementation. So anyone can use this to build a highly scalable machine learning system. A few other advantages is that it is really portable. So we actually have Android and I believe iOS implementations for TensorFlow. It's really flexible. As I said, not only could you use it to iterate on kind of custom neural network implementations, but you could also use it for totally different tasks. So I know that people are thinking of using TensorFlow for physics simulations. I know that there's an active effort to use TensorFlow for other machine learning models like regressions, random forests, this kind of thing. So you can potentially use it for a lot of tasks. And finally, it's open source. But that said, it is really complicated. And it becomes even more complicated when you think about how deep cutting-edge neural networks are becoming. So here's a neural network from 1998. It's called LinNet. It was, I believe, the first convolutional neural net, or at least the first successful one. And it is like 11 boxes deep. Each one of these boxes represents like a function, essentially. So the little model I was showing before with the flowing graphic would be about 3 boxes in this representation. So that's 1998. Let's look at what had happened by 2012. This is AlexNet. It was the first neural network to win the ImageNet competition. That's a big image recognition challenge. And since 2012, the ImageNet competition has been only won by neural networks. So over this period, it about doubled in size. The follow-on to AlexNet was GoogleNet. That was another winning ImageNet submission. And we can see it now. So like if you thought that the diagram that I showed on the other slide was complicated, just imagine if it were 100 times larger. And then, of course, this is 2014, so you can expect like that's ancient history at this point. The most recent one I have a diagram for is called Inception v3. This was our submission for the most recent ImageNet competition. The error rates for ImageNet have been decreasing exponentially. So at this point, it's basically a solved contest. We kind of need to find something harder to do with our time. But here is Inception v3. So the interesting thing about neural networks is they're like really good at solving problems. We would like to use them for some very important things. So one thing which Google is using neural networks for is the automatic reply generation in Inbox. I don't know if any of you use Inbox for your email, but it will try to like figure out what you want to say and say it for you. So okay, if we don't get what our neural network is doing, then maybe that's not so bad because it just like gives you a goofy reply and you go on with your life. Just don't send that. But we're also using neural networks for self-driving cars. And there we really want to be able to understand kind of a bit better what it's doing, really want to be able to debug it, really want to be able to monitor it. And the self-driving car neural network is going to be a lot more complicated than just an image recognition. I mean, this would be essentially a submodule in a self-driving car. So let's see what we can do about that. And the basic answer is we need visualizations. This is going to be a way that we can start to get intuition about neural networks and start to iterate on our ideas. So to that end, we've built a system called TensorBoard. TensorBoard is like a general purpose data visualizing system that is attached to TensorFlow. In this case, we have a very simple neural network that is more or less the same as the flowing graphic I showed earlier. Except now it's interactive and we can start to explore it. So maybe we can see, okay, you know, at the high level, we're going to have 2 layers. This layer is going to have a matrix multiply and bias add. And then there's going to be this ReLU function, the activation. Then maybe we'll apply dropout, and then it'll connect to layer 2. And at each step, we can now just check how is our neural network wired and start to get some understanding of what exactly it's doing. In this example of this MNIST model, like maybe it's overkill. It's simple enough that you could understand it on its own. But we can also apply it to this like crazy network that was so big that it no longer fits on my screen. And here, it just starts to be a little bit more tractable. Although this is actually a 44 megabyte text file that I'm loading because the graph is really that large. But now we can see that, okay, we've got kind of a corresponding structure where it's this tall tower, and then in each piece we open it up, and we can see that it's composed of these subtowers that are doing different things, and we can start to kind of explore. This graph does a lot of clever things to make it so that these really complicated structures can be rendered efficiently. We're actually publishing a research paper discussing all of the tricks we put into this. But one thing in particular is that it uses color coding to identify repeated substructures. So I can tell that all of these pink pieces are going to have the exact same nodes within them. And a little bit of history, when we first built TensorFlow, we had a hell of a time getting it to just do the right thing on the image recognition challenge. So there was a month and a half where we had built this really incredible system and it just wasn't working, and we couldn't tell, like, is this some minor bug that we need to fix because somebody made an oopsie typo? Or is there something fundamentally wrong with the approach to how this system scales that's going to cause it to get inferior results? And it turned out that in our ImageNet model, we had just had a little bit of a miscoding so that one of the layers was missing some crucial connections. And that's the kind of thing which now with this tool we would have been able to catch in hours instead of weeks. But we can do more than just visualize the network. We can also collect information about how training is progressing. So for example, maybe you want to track how your accuracy is changing over time or how the cross entropy is changing over time. Then TensorBoard is able to connect to your process and just record the data and show it to you as training progresses. And this all just fits into the same TensorFlow graph structure, which is to say that we have ops that do things like matrix multiplication. We have ops that do things like saving variables and updating them. We also have an op that exports data to TensorBoard. So that means that you really are free to come up with your own complicated metrics and insert them into the graph and then be able to track and visualize them. And here I just have a couple kind of simple examples. Another thing you might want to do is visualize images traveling through TensorFlow. It could be as simple as I just want to understand what does my input data look like. Or it could be that you're working on, say, a self-driving car and you want it to generate images representing its knowledge of what is in the what it thinks is in the road, so you can see what was it doing. TensorBoard supports that use case. Another thing it does is shows you distributions of data. So if you have some tensor that you want to visualize, you can save off a histogram. And I'm going to explain this visualization because it's a little bit interesting, and it's also a little bit bad. But I think it's a little bit interesting the ways that it's a little bit bad. So what the TensorFlow backend is producing is you can just serialize any tensor, and it produces this histogram where it has a bunch of really small bins showing the layout of the data. This was my first take at visualizing that data. And what it's doing is it's showing the evolution of this distribution over time, but it's only showing percentile summary statistics. So what I mean by that is that the thickest, we can take this as an example, or this slightly more interesting one. So here, the line in the center is showing how the median of the data changed. This area is showing how 1/2 standard deviation above the median changed. This is 1 standard deviation. This is 1.5 standard deviations. This is 2 standard deviations. This is the max. So it basically kind of assumes that your data is normally distributed and then shows you how that normal distribution changed over time. So sometimes this is kind of nice and useful. We can see, okay, this is the biases in the network, and the biases were kind of spreading out over time, but at the same time remaining contained. So maybe we can get some interesting intuition about what the system is doing. But the problem is that it really breaks down entirely on bimodal data. If we had a bimodal distribution like here and here, then because we're only seeing the top level summary statistic, it would just show up as a solid black box. So not really what you want. Also, I called it a histogram display, but it really is not showing histograms. It's showing these area charts. So I recently got a really fantastic colleague, wherever am I? Let's guess 45. Yeah. So I recently got the pleasure of working with this guy named Sean Carter, who joined the Brain team to try to build more useful visualizations for understanding neural nets. Before that, he did a bunch of work at the New York Times. He's also a music fan, and he saw this Joy Division album cover and thought, well, it's a nice album, but wouldn't it be a nicer data visualization? So what he did to solve the histogram problem was build this dashboard, where now we can see, we're still seeing the histograms evolving over time, but the direction of time is up. So each one of these slices is, I think, further in the past. So it's the present is here, the past is there. And now we can sort of get a sense, I almost view it like I'm viewing some mountain range in a beautiful distant country. But now you can really see exactly how the distribution evolved over time without losing all this information by treating it as though it's a normal distribution. And if my demo will work, I can even do So this demo has been really misbehaving. We'll see. OK, wait. I have a fix for this. I don't know why opening the developer tool is. Once it knows it's being watched. Oh, no. Computers, they're the absolute worst. OK, there we go. So yeah, I just think that's really cool. Like, I'm sure it'd be useful to someone, but I mostly just like watching this move around. In all seriousness, when you shift it like this, it becomes a lot easier to see how the differences relate to each other. So this one, it's like useful for seeing how it evolved over time, but really difficult to say like how tall is this compared to this compared to this. And on this view, you can't view it over time, but you can very clearly see how the shape moved. So between the two of them, I think it's a pretty useful tool, and we're going to put this into TensorBoard shortly. So yeah, that's my talk. I was worried I would come in under time, but it turns out I'm like exactly on target. And I'm planned to post these slides online at that URL. I'm not sure if they're there right now. The playground that I showed is going to be posted to the TensorFlow site, hopefully within the next week. I think if you watch Hacker News, it will probably show up there. And if you want to learn more about neural networks, I really strongly recommend Chris Ola's blog, because it's a phenomenal resource. And if you want to learn more about TensorFlow, we have a whole bunch of tutorials posted on our website. And with that, I would be happy to take your questions. Yes.
So I understand well, thank you. I understand how different nodes on the graph can show in TensorBoard what features are derived and debug that. Is there a way to use TensorBoard to debug vanishing or exploding gradient problems?
So the question was, can we use TensorBoard to debug the vanishing or exploding gradient problem? That's a really good question. Right now, I would say not really, but that's one of the things that I want to tackle. So we have a full development effort going forward on TensorBoard. One of the places that I would like to get to is using TensorBoard as a full kind of debugger for the TensorFlow system, where you can use it to, if you imagine using a regular debugger, the really nice thing is it lets you get in sort of in the middle of the computation and see what the state is and how everything relates. So what I want to do with TensorBoard is get to the point where you can set, kind of detect interesting criteria in how your graph is evolving, and then dump the full state of the TensorFlow graph and examine it in TensorBoard. So the way I imagine that would be working is like, if we could go into this graph and every point sort of click on an edge that represents a tensor and see the distribution of values there, so that when you have like a vanishing gradient, you can kind of see, okay, at which point exactly did it vanish? Or maybe if something goes to nan, like where did the first nan appear? So the answer is not yet, but we're working on it. Yes?
Do you know if any companies are using this in production?
I know Google is using it in production. I'm not sure. I suspect the answer is yes, but I don't know. Yes?
Can you use TensorBoard to visualize other graphical models, like Markov models or Bayesian networks, as like an educational tool?
That's an interesting question. So right now, the TensorBoard Graph Explorer is very tightly tied to the way that TensorFlow represents graphs. However, I do know of teams that have taken their own graphical structure and kind of turned it into a fake TensorFlow graph so that it would be usable in the Graph Explorer. So I would say like hacky, but possible. Yes?
Can you create, using the visualization to create your TensorFlow graph, like in a RapidMiner visualization building block that goes to creating the flow and just visualizing it?
Right. So the question is, can we use the Graph Explorer to create TensorFlow graphs? This is something we've talked about a lot because it would be really cool. It's interesting, right? People always want to have graphical, like GUI creators for code. And it's sort of a very mixed history at best. I can't really think of many tools that people actually use. But I think that's definitely something we'd like to try as an experimental project and see how it turns out. I think that particularly what we'll want to do is once we have a really stable patterns around how one sets up TensorFlow graphs, like wiring the input and output bits, then it would start to be more promising to have an interactive builder where you can like drop in a layer, choose the parameters for it, wire them together, and have that spit out the code. But it's not something that's on our near-term agenda as like something serious. I think that if somebody were to want to fork this and like try it out, that'd be extremely cool, and then that'd be a nice way to test it out and see if we should integrate it back in. Other questions? Yes.
So we started training a deep learning model at work, and we don't really have any other solutions other than throwing the kitchen sink at it and then like sort of taking things out and see where it starts to suck again.
Mhm.
Do you have any like suggestions on like trying to be smarter about like integrating new layers and like how they interact with each other, or resources for that?
I don't like empirically. That seems to be the way that everyone does it. I mean, I think it's a really interesting question. You know, even just hyperparameter search is a very difficult problem, and that's one thing we do want to tackle in TensorBoard is like giving the ability to just visualize how your hyperparameter search progressed, like what seemed to matter. I always just personally think it'd be really cool to try to leverage neural networks to figure out, like learn how to structure neural networks. But I don't have anything concrete for you. Yes?
How's the spiral doing?
Oh, great question. Wow, it got. Oh, you know what? I think that it paused when I was out of the tab, so it's because it's only on the 200th iteration. Yeah, we can leave this on as our background for any questions. Yes.
Can you also visualize the physical plan on the distributed system?
Sorry, could you say that again?
The logical TensorFlow plan, but can you visualize the physical plan?
Yes. Great question. I think that, let me, this, my link may not work because this is an internal Google link. But we do have that capability. And let's see if I can load it for you. Yeah, so actually I'll show a couple of other things we're working on. So this one is now visualizing by device, which I think is what you're asking. It's showing like the different colors represent which devices we've put the nodes on. So you can kind of see like, okay, this one is split between 2 different devices, and most of them are on the blue device, which is not really immediately meaningful to me what that is. We also have tensor shapes. So this is an example where you can see on each edge what is the dimensionality of the tensor that's passing through. We also have, we're starting to put in performance statistics into the graph. So here's an example where we can color the nodes by compute time. And we can see, okay, computing gradients is like almost all of the compute. And then as we dig into that, it's like maybe a particular matrix multiplication is expensive. Yeah, like this matmul is one of the most expensive ops in actually training this graph. We can also visualize the color by memory usage. And now we see, okay, really, again, the same matmul is by far the most memory expensive operation here. So yes, is the answer. Any other questions? All right. Thanks. Hope you enjoyed.